Welcome everyone this afternoon attending today's webinar entitled Today's Critical Mineral Technologies and How to Move Forward. This session is being recorded. First, I'd like to thank the sponsors for today's webinar, and it's made possible by the support of all of these folks: U.S. Department of Energy, the North Dakota Industrial Commission, Basin Electric Power Cooperative, BNI, Current Lighting, subsidiary Current Chemicals, Minn Kota Power Cooperative, and North American Coal. Thank you very much for your support. The presenters today are me, John Kay, and the person that's going to do the bulk of the talking today will be Nolan Theaker of the Institute for Energy Studies. So this is the second in a series of webinars that we'll be conducting concerning rare earth elements and critical minerals. The first webinar was held back in September, just as an introductory on what critical minerals were. Today is the second of those. The first one was also recorded. We have a couple of upcoming webinars in January, which will talk a little more on the business aspects. And then coming in March, we'll kind of present where we are as a whole concerning the core CEM program and what we've discovered so far about the future of critical minerals in the Williston Basin. So be looking for emails coming on those. So I'm going to run through just a couple of quick slides of information that was presented in the first webinar that we had back in September. And so the first thing is just to clarify as we're discussing. And so when we talk about critical minerals, the term critical minerals is an umbrella term. And so under that, we'll be talking more specifically about rare earth elements, which is a particular, well, mostly a particular row in the periodic table, plus a couple of extra elements. And here in a bit, I will show a periodic table to kind of clarify all of that. And then we have the critical minerals, and those are things, to put it easily, critical minerals are just those things that aren't rare earth elements. They all fit under the same general umbrella. And so examples of just critical minerals would be things like carbon or lithium or even magnesium, and there's many others. So keep that in mind as we're going through this. Generally speaking, when we're talking critical minerals, we're talking more about things that aren't rare earth elements. And when we're being a little more specific, we'll call out rare earth elements directly. So with that, of course, one of the big things that we wanted to really point out in that first seminar, of course, is that critical minerals are vital in everything that we do every day. And these pictures just give you some of the more simple examples of things that involve critical minerals. We use them on a daily basis. In my scope and line of work, I'm using them on a minute by minute and hourly basis. But one of the challenges with critical minerals, the vast majority of those materials are imported into the United States, and the supply chains involved in these are very vulnerable. And if you've been following at all what's going on with conflict in Europe, you'll see how the invasion of Ukraine and the effects that had on world markets. So world events can strongly influence the markets for rare earths and even their supply. Next slide. So we feel, of course, that the Williston Basin is the place to build an American supply chain for rare earth elements and critical minerals. We have the research expertise. We have the extensive experience in mining and energy development. The Williston Basin resources include one of the largest lignite coal deposits in the world. We have oil and gas production streams and other things. And our state governments have strong regulations that support resource development while protecting the environment. We have basin-wide collaborations that are in place that enable this to move forward. So we believe we're in an extremely strong position to advance rare earth production and critical mineral production and help provide security for the United States. Next slide. So if you look at this table, those elements that are in blue are what we're referring to when we talk about rare earth elements. And it's mostly that lanthanum line that you see highlighted towards the bottom, but also included in that is yttrium, and scandium is also talked about in the realm of rare earth elements. And when we're talking in general about critical minerals that aren't rare earth elements, we're talking about those elements that are highlighted in gray. So it's about half the periodic table that is referenced. Now, those elements that are highlighted in yellow are those elements that we feel have the greatest potential of availability in the Williston Basin to contribute that are marketable. So that kind of gives you an idea. So roughly, it's almost half of those elements are available in the Williston Basin. So coming up here in today's seminar, you'll be hearing about ways that we can take advantage of these sources, whether they're existing lignite coal mines, coal ash, which is a derivative of using coal mines, especially for power production, things like produced water from the oil and gas side. That's one of several streams from production that may be usable. But even going beyond coal and oil and gas, there are other things like shales, and there's a couple examples listed there in the bottom corner that also show potential. And we do have coal seams that are a little too deep to do, open mining on, but there may be some potential uses and accessibility of those through some in situ extraction techniques. And so that's kind of what we'll be covering today, or at least Nolan will be covering today. And so if you go to the next slide, then I would like to hand this over now to Nolan as he talks about technologies for critical mineral extraction and use. And again, Nolan is a technical group manager for the Institute of Energy Studies at the University of North Dakota. And with that, I will shut off my camera, turn off my mic, and sit back and let Nolan run the show. Take her away.
Thanks, John. And yeah, today we're going to be talking about some of the technologies we use. And generally, I'm going to be talking in relative broad terms. There was a lot of critical minerals. If I go through every technology and every step of the supply chain for all of those, we'd be here for a few weeks. So today will be broad terms, but should get you some information. So hopefully the slides advance. So some of the questions we're asking that we want to answer today on the webinar are, why do we need new technology in these for critical minerals and mineral extraction? How can we extract these critical minerals, both from somewhat of a business sense of coal extraction and co-products, as well as from metallurgy? What does metallurgy mean? What are the types, and how do we get it? And then in the supply chain, from those metallurgy concepts, we learn about what technologies are we going to use in that supply chain to get it from an ore in the ground to a finished product that will go into a cell phone or an F-35. And we're going to do a case study on the rare earths from lignite, specifically in this. And then finally, how do we move forward with critical minerals from a technology aspect? So why do we need new technologies? One of the premier reasons is because ore grade, or how rich a source is in a specific material, usually goes down. And if we look at from the 1850s with copper, we had 20 to 30% copper in what our ores would be for copper back then. Now we're down to 1%. We look at lead, 30%. Now we're down to below 5%. And so for all of these materials, obviously we're going to mine the most valuable resource first. And over time, those resources don't exist 150 years later with a lot more stuff. And if our processing cost literally increased with the grade, no mining would occur. I mean, if we had to mine all the materials and process all the materials using the technologies in the 1850s to make a computer today, the computer would be a few $1 billion likely. No one would own one. Now, additionally, not just in the grade, production rates dictate that we need scalable processes for mining extraction. This can't be done on the pickaxe and people moving carts around scale. This has to be done on the millions of ton scale, especially because rates of critical mineral use, specifically critical mineral use, are increasing. And what I mean by increasing is, in a lot of cases, the production of these critical minerals increasing significantly both to meet climate goals as well as for just general computer and electrification needs. These are the elements that go in your solar cells, your wind turbines, your computers, your power grid, your electric and gasoline cars. So all over the world, these are needed. And what this IEA report, the International Energy Agency report, says is by 2040, with just the base case, assuming everyone around the world is going to do what they say they're going to do for climate reasons, we need 15 times more lithium produced by 2040 than we do today. If everyone really wants to meet the Paris Agreement accords, we're going to need 42 times. And if we have solid state batteries, we're in the 50 times more lithium produced today than by 2040. And so for every lithium mine that exists on Earth today, you need 51 more of them, of that same mine, to produce what we need for these climate things. Look at graphite, 10 to 25 times, nickel, 10 to 20 times. These are substantial amounts of production for these that aren't accounted for. And so you need new technologies both to get these in a more efficient way, but also look for new ores for these. Additionally, there's some new technologies to reduce environmental impacts, and there's a few ways we can do this. One of the ways is valorizing or making value from existing wastes. John mentioned coal ash and produced water as environmental challenges that currently exist, but if you could generate a product from these and make value from these, those would obviously be very significant. Another one that's being done around the US is acid mine drainage and trying to get rare earths and other critical minerals from that. Another way you reduce the environmental impacts of new technologies, maybe you use new technology that's a more benign process. It either uses less chemicals or less toxic chemicals, and just less means there's a smaller spill risk. There's no nasty organics getting into aquifers. There's no acids draining into rivers if spills happen. Obviously, it's a terrible thing. No one wants that to happen. But the smaller the quantity that you have, the less risky it is, both in terms of how damaging it is and how likely it is to occur. And third, a number of other technologies are looking at energy conscious methods. So no longer assuming that essentially infinite energy exists and whatever, I can just burn coal to produce heat or other means. And so I can lower my power and fuel requirements for some of my existing technologies, which means as that ore grade goes down, and in 10 years, I have 20% less of my mineral in my ore that I'm mining. In essence, my cost doesn't go up because I found a technology to, in essence, use the same amount of energy. Additionally, as I mentioned earlier, and as John mentioned with the other ores that we're looking around in the Williston Basin, we're looking at new technologies to use these unconventional ores, and there's a lot of advantages for that. So some of these ores might have a lower content of these critical minerals than some of the existing just hard rock ores you might find in some mines, but they might be in a more accessible form, like what we find with the rare earths and lignite. Additionally, you can have co-product options, which can help stabilize economics and offer some technological and business advantages from making more products from the same material. And you can also reduce the environmental impacts of other sources that we've talked about. Additionally, unconventional ores can have some significant business benefits. Once again, in some of the environmental challenges like coal ash or acid mine drainage, obviously there's a lot of business benefits and permitting benefits to reducing the environmental burden that I have and getting these critical minerals out. And even away from that case, if we're just looking at for instance, the lignite, still extracting rare earths and critical minerals from lignite, I don't have to permit a new mine. I don't have to build a new mine. I don't have to get all that equipment. It's already there. And so there's a significant business benefit to approaching it that way. And some examples I've already mentioned are these rare earths and critical minerals in the lignite and the built-in byproduct, the lignite that comes with it. And then also lithium and magnesium from produced water, where in essence, we're not only reducing the environmental burden and challenge of this produced water, but we're also making value from it and making it a product rather than a waste. Now, how I'm going to do my extraction, there's a few different ways that I can look at it. One of the ways is, what ore do I have, and how easy or hard is my critical mineral to extract from that ore, and then what impurities exist in that ore. Hard rock ores, like in this case, which is monazite for rare earths, they have a lot of rare earths, such as 4 to 5% rare earths, but they're relatively difficult to extract. It takes a lot of concentrated acid, takes roasting, very water intensive process, and they can have some harmful impurities with them. So then are either hard to separate from or can be permitting challenges. And then lignite, we found is a different form than in the monazite ores. It's easier to extract those rare earths and critical minerals. And so there's benefits there, even though it is a significantly smaller percentage of rare earths. And so what ore I want to look at will determine what technology I need to use. Also important, and potentially more important, whether the critical mineral is the dominant economic interest is important. Most of these critical minerals are byproducts from other processes and aren't the target themselves. And there's significant benefits from joint processing of these ores. So going more into detail on why this co-production concept is important and how it makes critical minerals possible in today's world is many critical minerals are just too rare or dilute to really economically recover individually. And you can think of this on the order of a teaspoon per ton. I mean, 20 of those 55-pound bags of salt or flour that you're going to buy, there's a single teaspoon mixed among all of them, and that you have to try and recover out of there. And that's going to be challenging. But if the critical mineral exists with another mineral that I can extract, it can help reduce the cost. And this is done with copper, aluminum, iron, primarily around the world. And one example of this is the world's largest producer of rare earths. The single largest production source on the planet is from an iron mine, Bayan-Obo in China. And the rare earths were in essence a byproduct produced from mining for iron ore. Now, going more into detail, the case study I want to give you guys is gallium. Gallium is this metal that melts in your hand. No, it's not mercury, but it melts in your hand at skin temperature. And it's used in solar cells, LEDs, lasers, a lot of really high-end computer and energy applications. And the market's not going to go down on those. Those are going to increase in market. Now, the average content of gallium in the Earth's crust is only about 18 parts per million. That's really difficult to extract economically on its own. And once again, the teaspoon per ton basis for gallium, it's actually not even a full teaspoon. It's just 3/4 of a teaspoon per ton. Very tiny quantities. But when I process aluminum, I concentrate gallium up, actually 10 times during my aluminum processing. And I actually spend the chemicals to dissolve it. It's already in a solution form in my aluminum processing. So I've already spent some of the costs on extracting it and concentrating it. It's 10 times more. So then it makes a lot more sense to get it from that area. And so as a result, essentially all the gallium in the world comes from byproducts of aluminum and some zinc processing plants. And it's not mined for itself. Next, I want to kind of get into what technology areas exist for processing these critical minerals. And then in essence, I'll go into where those technology areas fit in the supply chain. And the 4 primary areas of extractive metallurgy are mineral processing, physical processing minerals, crushing, grinding, size classification, etc. Just physically breaking the rock, but not necessarily chemically changing it. Hydrometallurgical, the word hydro in there, meaning water or liquid solvents to extract and separate these critical minerals. Pyrometallurgical, or the use of temperature and heat to separate minerals or form products. And then electrometallurgical is the use of electricity for separation or processing. All those names, they're relatively non-inventive. So in mineral processing, the physical processing and handling of these constituent minerals is what that means. And what the size classification on this: crushing, grinding, screening. This is just taking big rocks smaller, making them smaller, and then separating them based on their size. No chemical impact associated with that. It's just crushing and grinding. And some separation can occur in mineral processing, and this is density separation, or how dense is one mineral compared to another. How easy is it for one mineral to grind than another? If I have a mixture of two minerals, one's very hard to grind, one's very easy to grind, the easy to grind material will end up being far smaller than the harder to grind material after I grind it. And so then size can separate the two. And also wettability. Do the minerals behave different if there's water or something put over top of them? But these are all non-chemical processes. These are all just touching and physically handling the rocks themselves. And one of the classic examples is gold panning. It's a form of crushing, somewhat screening, and density separation, where I just take a bunch of the silt in a river, which has dense gold particles that are harder and stay bigger, and then light clay particles that kind of break up as I shake them around. And in essence, as I pan, I'll slowly have the gold particles fall to the larger gold particles fall to the bottom, the lighter, smaller silt particles fall off, and that's how that works. Also, for combustion of the pulverized coal combustion, the act of pulverizing coal is a mineral processing, just making it smaller so that it will work for combustion purposes. There's also mineral concentrating spirals. There's a lot of different technologies in here, but as a note, mineral processing as a whole field is only really applicable to rocks, to physical solid minerals. It's not going to apply really to solution ores like produced water or brines. And mineral processing, I mean, man has been making big rocks into smaller rocks for probably about 12 millennia at this point. This is a very, very old technological field, but there's still new things occurring in this field. Now, in the hydrometallurgy space, once again, this is solvents, acids, and bases to separate critical minerals from other materials. And why I want to do this is, A, liquids can be moved around easily. Once again, man's been moving around liquids since irrigation 3000 BC without manual labor. And in essence, just the liquid will move itself. We've had pumps for very long periods of time. Liquids are easy to handle. Rocks are a bit more challenging to handle and move around, and there's problems with that. Another thing is hydrometallurgy is extremely powerful. There's many separation methods exist. Literally thousands of extractants and acids and bases exist in these liquids. And so I can separate pretty much any one element from any other element on the periodic table using hydrometallurgy. Now, the cons of it, there's obviously, if I'm using lots of water, I'm both withdrawing lots of water from a potential watershed or reservoir, which has environmental effects. I'm discharging potential wastewater either into that same area or somewhere else, which would have environmental effects. And I'm using these costly and hazardous chemicals. In some cases, obviously new technologies want to reduce that, but typically you can't get fully away from them. And there's effects with that. And additionally, hydrometallurgy can essentially not form metals. It isn't going to be, you aren't going to make the entire supply chain hydrometallurgy, but it's a really powerful separation step. And some examples of this, nature uses this same processing method to make a lot of different minerals. Limestone is made when water and CO2 contact calcite minerals. You get your massive limestone we use in quarries. Pyrites, fool's gold, is made from iron mixing with the sulfur gases at deep ocean vents. And then also our theory on how the rare earths are in the lignite is potential capture of the organic structure of the lignite, capturing these rare earths as the liquid moves through. And they're all examples of just natural hydrometallurgy where no man-made thing needed to happen to have these happen. And to tell you once again how powerful hydrometallurgy is, pretty much every element in the periodic table is extracted and separated using some form of hydrometallurgy. There's very few that aren't. Typically the ones that aren't are gases like neon. And this is leaching of copper is one of the first really in-depth hydrometallurgy pieces that happened in the 1200s. This is very old technology still. Now, pyrometallurgy, use of thermal and pressure processes, heat, to separate and chemically and physically alter these materials. And there's advantages to doing that. First, there's almost little to no dependence on any chemical, which is good. There's many possible sources of heat or process gases that exist, be it electric heat, coal heat, natural gas heat, hydrogen heat, indirect heat from steam, many different cases. And so there's a lot of power behind pyrometallurgy. However, it's not a very robust separation method. What I mean by robust in this case is it is not able to separate all the elements of the periodic table like hydrometallurgy can. Some separation can happen from it, but it's typically limited to either small separation effects or the really ultra pure separation, where in essence I'm removing 0.01% of impurity from a material, and pyrometallurgy can do that. But your common separations can't really be done this way typically. Additionally, moving hot molten metal is difficult. Things that are within a certain factor, like half the temperature of the surface of the sun, that doesn't like moving around. And anything I put that in has to obviously be able to withstand that immense heat. And that's a huge challenge. Some of these examples, the prototypical one is iron and steel making, where I mix carbon-rich coal, the coke, with iron ore, and I'll eventually form a somewhat pure iron metal. Once again, this is only like 90 to 95% pure. So for a lot of critical minerals, that's nowhere near pure enough that you would need. But it still gets you from an oxide in an ore that's only about 60% to a 90% pure metal. And so it can change the form of the material. And for critical minerals, germanium, gallium, and titanium, I'll use a chlorine-based pyrometallurgy process where I'll, in essence, mix just the rocks with chlorine gas, heat it, and then boil off the critical mineral chloride, and I'll eventually get my pure critical mineral that way. Electrometallurgy, the last field, is the use of electric potential to chemically alter or separate these materials. And it doesn't always have to be a direct electrical use. Now, the advantage of electrometallurgy, it can do to metals what hydrometallurgy can do to separation, where it's very powerful. It can metallize virtually everything. Only things that in essence form a resistor in the metallic state, which some do, can't be used for electrometallurgy. And typically there's very little to no direct environmental impact from electrometallurgy. These solvents you use and these electrolyte solutions you use, they can be relatively harsh in terms of what's in them, but they're typically fully reused, if not 99.9% reused. And so there's very little environmental discharge from electrometallurgy processes. Now, a con of this is it can be extremely susceptible to certain impurities. Once again, those resistive elements I talked about. And it can also be extremely high electric demand for some of these things. For instance, copper. And some examples of this, so the common example a lot of people, not really anymore, have is silver and gold plating on silverware. And this was just, in essence, I'll put like a brass spoon into a solution that has some silver ions, apply an electric potential, and then I pull out a silver spoon. Silver is just on the surface, but it's that same concept. And electrometallurgy in this critical mineral world is used for making metals for over 30 different elements, the rare earths included. And typically this is molten salt metallization, where it's just really hot, and then it's the rare earth chloride, for instance. But sometimes you can get away with putting it in water as well, like for copper, for instance. So now that I've kind of talked relatively briefly about the technology fields that exist, I'm going to kind of mention where they go in this supply chain. When we talk about a supply chain for mineral processing, it doesn't typically involve the same things that supply chains maybe for beer, the common or the prototypical beer game example for supply chains, where it's the brewer and the the wholesaler and the warehouser and the distributor and the consumer. Those distributors don't exist for us. It's typically just all the processes to get from ore in the ground to a finished good. And that's mining, concentration, separation, processing, and then manufacturing. So for the mining technologies, this is the process of getting a high value ore to a surface. And what this includes is exploration technologies. How much ore is down there? Is it valuable enough that I want to go after it? Or extraction technologies, and that's how do I physically dig it up in a way where I don't dig everything else up as well? This is where the solution mining or those in situ mining where I just pump solution down and then pump it back up with my material in it. That's where that exists. And also in mining is the sorting technologies on once I dig it up, how do I make sure only the best ore, I only process the best ore and the low value ore that's just going to waste chemicals. I don't use that, and I essentially just put that back in the ground where it came from. And mining technology is pretty much all mineral processing. These are digging rocks up. For ore concentration, this is mineral processing and hydrometallurgy, and this is making these valuable components in this dilute ore more pure. Typically, it's not the right purity you want or in the final form that you want. Like, for instance, this will be less than 5% ore to about 90% concentrate, but this still isn't, you aren't going to make a product with what comes out of ore concentration. And typically, it's designed for removing those impurities that are challenging to refine. And this, once again, involves the physical mineral processing and chemical hydrometallurgy means of ore concentration. And more often than not, they're both methods combined for a single processing method. And once again, the process is designed for the feedstock. The example I used earlier where a hard rock ore is going to be very different than a lignite and the technology you use. Even certain other hard rocks, not all hard rocks would even be the same. And so you really have to know what ore you're getting to design the process around it. For separation, here we're generating a high purity material, separating out all the other constituents in that concentrate. And typically a number of separation approaches exist, but this is all still hydromet technology typically. Every now and then, some pyromet and electrometallurgical technology exists, but it's primarily hydrometallurgy for the world. And the ore feedstock really only somewhat affects the processing technology. Some impurities, like I mentioned, in electrometallurgy, some impurities won't work, but typically anything will work. Then in processing, here we're converting the high purity material into a usable form, such as an oxide into a metal, where now it'll be usable in potentially a final form. And typically this doesn't involve a substantive purification process. This is just turning the oxide into a metal or something like that. And typically this is ore feedstock agnostic. Whether this came from a hard rock or from lignite doesn't really matter at this point because the purity was set by the separation process and it isn't really going to affect your processing anymore. And then in manufacturing, here where you manufacture the components that are saleable in these many industries, the magnets, electrical components, graphite, carbon fibers, etc. And those are the components that will eventually go into the final products, the cell phones, turbines, F-35s, etc. And here the process does become feedstock conscious again, not usually for a technical reason, but for ESG, Buy America reasons, etc. Now, the case study I want to get through relatively quick at this point is rare earths from lignite. And here we'll just essentially step through the mining, through the manufacture, mining through processing at this point. Mining, rare earths are typically concentrated at the tops and the bottom of these seams. And so we have to explore for the rare earths throughout the mine area, tops and bottoms of the seams. We need to remove and recover these rare earths from the existing mining plan, and sometimes develop a new technology for surface mining if we're looking at thin seams or layers. Once again, this is top foot to 2 feet at a maximum thickness usually for these high rare earth layers. Also, we can look at this for separating the rare earth rich materials from the combined coal stream with some on-belt analysis and sorting. And here's a picture of the Falkirk mine and one of the new mining technologies they've deployed for reclamation purposes and some drone assisted analysis methods. Then in ore concentration from lignite, we're going to be using hydrometallurgy, and this is extracting the rare earths from an ore using an acid. Now, if I was using a conventional ore like monazite, it'd be concentrated acids, whereas in lignites, because it's organic bound, I can use some dilute acids. And once again, this is in that unconventional ore territory. Then I'll precipitate the rare earths as a solid, typically some form of a rare earth salt rather than an oxide. And then I'll, in essence, burn that salt, calcine that salt to convert the salt to an oxide. That way it's easier to process for separation purposes. In separation, the two main paths that kind of exist around the world right now is the primary one is hydrometallurgy, which just solvent extraction with organics or ion exchange extraction. And these, once again, very powerful separation technologies. They can get these things very pure, but they require lots of organic mixer settlers. And then there's some impurity. Typically, they can handle just about any impurity, but they don't tolerate changes in those impurities as you go time by time. So if you have different impurities pop up in a different section of coal, some of these processes are more intolerant to that than the other option of electrometallurgy, where you in essence electrowin or that separate with electricity these individual rare earths. And these impurities can vary. They're more tolerant on how variable the impurities are, but some of them can in essence be process killing, and you'll have to switch to the hydrometallurgy paths. And then finally, in the processing and manufacturing, here we've got the making of rare earth metals, and the two main paths you do that are electrometallurgy, which is the current global leader in producing, where as a result of the production, there's some major environmental controls that are needed for processing the gases that are produced during that process. Part of the reason why this doesn't typically, why this isn't occurring in the US right now, is we're looking at some ways to improve the environmental behavior of that. And then pyrometallurgy, or reduction with another more easily electrically formed metal. So I don't have to handle these environmental problems and the heat and the high electric usage for the rare earths, but separating the metals from each other can be tricky once I add the second material back in. So finally, how do we move forward? And looking at all these technologies, there's lots of different technologies. In each of those technology spaces, we need to evaluate it with what ore do we have? And so what type of ore is it? What impurities are in there? How much of that ore is it? And then how big is that ore? Is it millions of tons, or is it a few thousand tons, or is it really tiny? And the technology I use is dictated by all four of those things. Then also, is co-production possible? Can I produce these critical minerals with something else, or can I produce other value from this same process? And what technologies allow that or disallow that? Now, additionally, the current technology scale, is it commercial and trusted, or could it be a decade away but make some significant impacts in economic or environmental benefits? Then also market needs. Does the technology produce the product that we need now or in the future, or does it produce the wrong form or something like that? But really, all of these technology questions are business questions more often than not. It's risk benefit analysis on these new technologies, these that I talk about that are always better. Do I want to take in some of these cases for mining and mineral processing, do I want to take $1 billion risk on a new technology that could be better rather than one that's been proven for decades? Do I, instead of these co-product options, do I simplify my process to make one or two products instead of making many products? And there's a lot of questions that go into that on, are these other possible products always going to make me money, like in the rare earth case, or are there times where they might not make me money because of either price fluctuation or just the lack of supply chains in favorable countries. What product is going to be the primary product? And so that will dictate how I process these things to make sure I get the primary product that's always going to make me money, rather than a secondary one that I might have to stockpile for a year or two waiting for the price to finally return. What's going to be the first product I make, which may or may not even be the primary product in my economic evaluation? And then ultimately, who's my buyer and what do they want? Who wants what form of the product, and how do I make that product for that buyer? And so, kind of in summary of this, why do we need new technology? We talked about ore grade and production rates and why both of those dictate new technologies being required. How do we extract these rare earths? We went through the co-extraction with a major element, such as gallium with aluminum, and also a review of extractive metallurgy and what those technologies fields involve. What technologies do we use in this supply chain, from mining to manufacturing techs and all versions of those 4 extractive metallurgy technologies, and then went through a case study of the rare earths with lignite. And then how do we move forward with critical minerals, and the questions for new technologies and what they have to answer based on ores and others, as well as the business challenges associated with them. And with that wraps up mine, and I think I'd turn it back to John Kay at this point.
Yeah, thank you, Nolan. Appreciate all that. That's a lot of information in a short amount of time, right, everyone? So it's a lot of stuff to go through. And I think Nolan had mentioned we could spend days talking about this specific stuff. So this information today is being done through a program funded through the Department of Energy called the Core CEM program. And you can see there what Core CEM stands for: carbon ore, rare earth, and critical minerals. And their main goals of the program you see listed there, and certainly those of us that work within the Williston Basin say that we easily meet all of these things. And certainly we're looking for economic growth and job creation. And we want to be able to utilize our resources and a little more specifically our lignite resources far beyond just energy generation. And we want to be part of that domestic production of those rare earth elements and critical minerals. And of course, we want to be part of strengthening our national economy and security. We are one of 13 programs across the US directly affiliated with the 13 basins, as you see noted here, across the United States. We're number 6, in case you're not geographically literate like I am. I take a while to find these things, but we're number 6. And with our team for the Williston Basin Core CEM Initiative Program, you see we have a lot of support that extends even far beyond our region. And I'm very thankful for all of this support and interaction that goes not only with industry, our universities, governmental systems, but even along in integrating and having discussions with other Core CEM teams across the US. There's a listing of all of those. Again, I just want to thank one more time our sponsors for this program: Department of Energy through the National Energy Technology Laboratory, of course, the North Dakota Industrial Commission through their Lignite Research Program. Power companies, want to point out Basin Electric Power Cooperative and Minn Kota Power Cooperative, who are providing financial support. And of course, 2 coal companies in the region, BNI Energy and the North American Coal Corporation, and additional support and advice and direction through Current Chemicals that are also helping us steer through all of this information. Thank you to all of those sponsors. And then just real quickly here, because it's a federally funded program, of course, I just have to point out that things that are talked about and expressed today are not the direct opinion of the Department of Energy. And if we did bring up specific products, we're not bringing them up to promote them through the course of our discussion. And the same goes because of our financial support through the state of North Dakota and the Industrial Commission. Those same general points stand as well. We're not promoting, and they're not, directly supporting any products or techniques that we're talking about today. So one last reminder for all of you that we do have 2 more scheduled webinars coming up, one in January and one in March. And we have a QR code here, or you can see listed at the bottom of this slide, our address on the internet to get to our website for the program. We've recorded today's seminar. We've recorded the first one. First one is available on this site for you to view. And today's presentation will also be put on that website as well, in case you want to go back and review something. Or if there was someone that you know that wasn't able to make it today, please pass along to them that these webinars will be available online that they can view at another time. So with that here, we'll open it to questions. If you didn't type one already, but one pops in your head now, please go ahead and present those.
Can I ask a question?
Absolutely. Go ahead, Pat.
With the need to import so many of the critical minerals, what's the role of research in coming up with substitutions? Possible, not possible, no research?
I can take that one. There is significant research in looking for substitutions for some of these elements. There's been a lot of research in looking up new magnets so that we don't have to depend on the rare earth magnets. But for a number of these elements, despite decades of research, we still haven't found a good alternative yet. It is still pretty much the only one that works. Like, to use the magnets as an example, if I recall, some electric vehicle manufacturers were looking, well, what if we went with a different magnet than rare earth magnets in my EVs? They found that the range got cut by 40%, which is pretty severe for already one of the major drawbacks of EVs as they stand. So in some cases, there have been substitutions. Often the substitution is with a different critical mineral, and so it just offloads the problem of importation from one to another.
And Nolan, correct me if I'm wrong, right? A lot of this research takes a long time. And it's not that there aren't other solutions to some of these needs, but it takes time to develop them properly. And so certainly for now, the ones that we've been talking about today are the most readily available, but it doesn't mean that research is not being conducted to improve and change what those potentials are down the road.
Well, if I could too, Representative, the smart guys working the technical side, we're thinking a lot about DOD might be a likely place because the cost benefit goes out of it a little bit, but we're just trying to do a really good assessment of what we have in the basin and then trying to develop the business side somewhere else.
This is Shane Adelman, Pacific Northwest National Lab. What Nolan and John had mentioned, it is extremely difficult. Pacific Northwest National Lab has had millions of dollars of direct line funding to develop catalysis that don't depend on the rare earths and use common things. Iron is a really attractive component because it's cheap, it's redox reactive, it simulates a lot of the things that rare earths could do, but they've been at it now for 20 years and they're making progress, but they still don't have anything that's even close to commercially viable.
It would appear we need a serious crisis then to generate more research.
Research will solve perhaps some of the long-term issues. In the immediate term, we simply need more domestic sources of the critical materials. The research won't put anything into the supply chain quickly.
Well, I guess I was thinking back like World War II with our critical need for rubber. Suddenly we found a synthetic that worked really pretty well for the most part. So if we are importing so much from China, you would think there would be some motivation.
Oh, there's lots of motivation, but the solutions for a lot of these materials are not easy. I mean, going from natural rubber to a known organic reaction, pretty straightforward, but these problems have been looked at for a long time. And I'm not saying they can't be solved. We'll figure them out. We're clever, right? Lots of smart people in the world, but the low fruit has already been picked. The easy solutions are already out there. Do we need to make an investment? Absolutely. But it would help tremendously bridging until we find those new solutions to find new domestic sources.
Well, we have such a huge deposit of lignite in our area. Anything more that they can pull from that resource that might fill some of these needs?
Absolutely. That's what everybody's been talking about. It's a tremendous resource.
And that's what we're looking at, is trying to get these critical minerals from lignite, or from lignite ash, or from produced water, or from all the resources in our basin. But it's not overnight kind of answers. That takes time to be thorough and make sure that, yes, what we're doing will extract what is actually needed, and not just something that looks nice. And then also it will do so in an environmentally responsible and economically feasible way.
Well, I think, Nolan, you just hit it, that the economics and the environmental rules, we can't compete with China right now. And so back to your point, Pat, about a crisis. I mean, if we get a buyer willing to pay what would take to make it pencil out in North Dakota, we could do it. But that buyer's got to be like guys that make fighter jets or weapons or something like that, or Teslas. So I think we just got to keep working both sides, the business side and the research side.
I mean, we don't use slave labor here in the United States, unless you count student interns. And the environmental rules in China are so abhorrent that you can see the runoff from the rare earth mine from space. Literally, you can image the runoff from that big deposit that Nolan was talking about. And it's so bad, the iron and other mineral runoff, you can see it changing the color of the rocks in the streams from space. We probably can't do that locally.
Any other questions, comments from anyone? Love this discussion. Okay, and the pathway discussion is also a good leader once again into, stay tuned for our next presentation in January, where we will talk a little more about the business side and what that might potentially look like. So good discussion here this afternoon. Appreciate everyone being online here today for our webinar, and we look forward to seeing you on the next one. All right, thank you, everyone.